Yes.
Reionization with Saleem Zaroubi.
Thank you. Thanks first for the invitation, Rosaire, Roland, and the rest of the organizing committee. It's a pleasure being here. This is the first time I'm in a school here. I've been here a couple of times in conferences, and it's always wonderful. It's beautiful. So I was asked to talk about 21 centimeter, and then I realized that most people have nothing to do with 21 centimeters. So you are probably the only one I know that do simulations from the theoretical side. So that's fine. So which adjust a little bit my purpose of these talks. The first part of so I'm giving an hour and a half today and an hour and a half tomorrow. Today I'll focus on the basics, basically just for you to know what are the issues, the basic physics stuff, and I hope you have fun with it, even if you don't work with it. At least you understand when we talk about 21 centimeter, what are the issues. And tomorrow I'll talk more about the observational side. Okay, so that's the plan. And there's lots of literature. I listed a few of them. Some are kind of older than others, and they are not exhaustive because during the talk I'll have a lot of references as well. This one is anyone interested in the topic, I recommend this review quite highly. That's this is old now, about 20 years old, but that was one of the kind of people started thinking about this. I'll talk about the history of the topic a little bit. This is something I wrote about the Epoch of Reionization also long ago, 2013. And you have, this is basically pure radio astronomy, which you might not be interested in, but if anyone is interested, especially in interferometry, this is one of the standard references. And nowadays there's lots of instruments that all have their own websites, and they have their own publications, so these are the main ones. Of course, there is much more. So the plan today is basically the theory, the basic theory, and these are the topics I will cover. They are in the agenda. So let me start with history. I love history, so I think we normally kind of get it out. History is good to get you in context. This is one of these fascinating lines. It has lots of history. I will not spend my time talking about history, but at least I have to give some dues to some people. This line was predicted in 1944 by Dutch astronomers. They were under Nazi occupation at the time. It's amazing what people can do under such a pressure. I can relate to it for some other reason, but and the story starts with this guy, Jan Oort. It's the famous Jan Oort. The Oort clouds, or parameters, and all of that. He was teaching in Leiden undercover because the Germans at the time decided no one should go to university. So it was an undercover situation. And this guy was a student in Utrecht whose advisor, I forgot his name, was a communist. So he was in jail. So he basically was coming to these, and then Jan Oort realized that he's a bright guy. So he asked him to look at forbidden lies at the time, quantum physics. This is, again, this is 45. Radio astronomy just started before the war. Jansky had his thing in the late 20s, and Reber, I should say, had his own kind of discussion. So people started getting just interested in the early 30s. But then Europe was really going, there was a mood that we are going to war. People stopped talking about this. But then Jan Oort, in this conditions, asked Van de Hulst to think about forbidden lines in quantum physics. Quantum physics was brand new. You think it's forever. 1925, 100 years ago, exactly, the first paper on quantum physics was published. So this is really brand new. This is like me listening 10 years ago to a talk by Andrea and digesting it, taking me 10 years to digest what it means. It's really early days in all these aspects. And this was the first. So there was the forbidden lines, and there are many of them if you look at the paper. And he published his paper in this, it's called Tijdschrift. The kind of Times of Writing or something like this. Magazine, exactly. A magazine of something. I forgot. It's in Dutch. Nobody knew about this. And suddenly, after the war, it was kind of published that the Dutch had discovered this line, 21 centimeters. So he looked at many lines, and the most interesting one was the 21 centimeter line. And he predicted that the galaxy will have a bright thing, right? Our galaxy should have a lot of 21 centimeter. And immediately after that, there was a kind of a rush to try to observe it. And the first who tried was this guy. He built a telescope out of old German radar batteries. So again, it's after the war. There's nothing. So you use it. And they were going to find it. They were really very close. But he had a horrible engineer. And the engineer was really bad. So and this topic of radio astronomy is very close to engineering. Very close. So unfortunately for them, there was a fire, and it took them a few years to recover. By then, a team from Harvard beat them to it. And that's Ewan and Purcell. And they published this first paper of detecting 21 centimeters from the galaxy in 1951. And that was a big deal. These guys, which is Oort and his new engineer, published immediately after them. And you notice that this is Nature 168356. This is Nature 168357, just a page after. Actually, they waited for the Dutch to have their detection before. Nowadays, this will never happen. We rush to publish to be the first. They gave them their respect. But in many ways, the association already, although he is the guy who predicted, 21 centimeter history is much associated with Jan Oort. I'll show you why in a second. Then there was this, again, this is in Dutch, this is pronounced Wouthausen, right? If you are Dutch here and I'm doing it wrong, please correct me. He was a physicist at Amsterdam. He has an effect in particle physics. He went to Oort and told him, what can I, is there something interesting to do? And he said, yeah, you can calculate excitation mechanism. And he wrote a paper. I'll show you the paper. I think I have it here. This is the paper that Wouthausen wrote. This is the whole paper, 3 paragraphs, right? So I'll come to that. I'll tell you the details of that a little bit. All what he said in this paper, that you can excite a line. We have a line. We'll get to that. And you have to pump it, excite it. I said, Lyman alpha can do that. Go up and down. I'll explain it. This is all what he says. There's no calculation whatsoever here. And then, immediately after that, was a series of beautiful papers by George Field. I think we just talked about him over lunch. Apparently, he was Andrea's advisor. I didn't know that until today. He was maybe 22, 23, I don't know, very young. These are the most beautiful papers I've ever read in astronomy. They are so clear, so the physics, he lays out the physics quite clearly, the derivations quite clearly. And then they were forgotten for many years until we came to the cosmology. They were forgotten because in galaxies, most of the effects he talks about are not very significant. They are the pumping is quite easy in galaxies. And that's the reason. Now, in cosmology, so this was done for galaxies. We have H1 in galaxies, right? There's lots of H1. So in cosmology, the first thoughts about its relevance to cosmology was in the early 70s. And that was kind of inspired by Zeldovich's top-down approach. If you remember, if you have had a course on structure formation, there are 2 ways to look at how structure works in the universe. Either bottom-up, what we call now hierarchical structure formation, or top-down. Pancakes, you remember the pancakes? So that's because of Zeldovich approximation. And actually, if you look at the details of the small scales, the first thing on small scales, even in the hierarchical structure formation, are pancakes. Yeah, so these are the first things that you can see. But he was predicting that you should see huge pancake on the sky, and then people started looking, maybe H1 is there, and we can look at it. Of course, very quickly after this, the CDM started, and with CDM you have hierarchical structure formation, bottom up, and that was. The other person I want to give credit for is this man, Martin Rees. Martin Rees, way before the rest, started writing, or roughly every 10 years, there is a paper about this topic from Martin Rees, about the importance of 21 centimeter in cosmology. There's a paper that I haven't mentioned. There's a paper before this, 8 years before this, with Hogan and Rees, if you remember. For those of you who read it, who talks about this. This is more important, 92. All of them said, okay, it's there, it's very hard, until he hit gold. Piero Madao was in Cambridge. Avery Mikeson was close by. I think he was visiting. And they wrote a paper about 21 centimeter in the universe, in the IGM, and how we can detect it. This is the forming paper of my field, right? This is what kind of set all the standards. The rest are kind of, we are built on this. This is the most significant one. There is another significant paper which was written in, shortly after this, 1999, by Shaver, Madao, De Bruyn, and Wickling, I think his name, that showed from observational point of view that this can be done. And I'll tell you, during this, these two lectures, I will kind of explain what are the difficulties that they were trying to explore in this paper and the advances. After this, there is a huge rush. There was a huge rush to build telescopes to detect 21 centimeter at high redshifts from the IGM. So this is the form. I mean, these are the two important papers. There's lots of other important papers. I don't want to kind of minimize the contribution of anyone, but these are really the first ones. And now we have a number of telescopes that are kind of geared towards detecting 21 centimeter from the Epoch of Reionization and before, cosmic dawn and dark ages. And so this is the history. It's quite an interesting history. The World War I, II history is quite interesting. There's intricate details there. If you are interested, there are books written about this. It's very kind of very nice. The line is a hyperfine line. It's a transition. It comes from an interaction between a spin-spin interaction between the proton and the electron in the hydrogen atom. It has to be anatomic hydrogen. Molecular hydrogen doesn't have that because the molecular aspects, the vibrational and rotational modes, take out away from it. This transition is very rare. This is the ground state where the two are anti-parallel. The spins are again, not parallel. And this is the excited state where the spins are parallel. And this has an energy difference of 21 centimeter photon. That's the story. That's why we call it 21 centimeters. It's very low energy. And the probability for this to happen, the lifetime of this transition is about 10 million years. So you have an excited kind of state until it goes down, it takes 10 million years. The issue is that we have so much hydrogen in the universe that you see it all the time. And the whole game, so let me explain another things here. So 21 centimeter, that's the frequency, 1,420 megahertz. So it's 1 gigahertz, roughly 1.4 gigahertz. When we want to look at redshift 10, this will be redshifted by a factor of about 10, 11. This goes to 140 megahertz. So our measurements are in the hundreds of megahertz to tens of megahertz frequencies. This is not just radio astronomy. This is the low-end frequency of radio astronomy. And it's darn difficult. You will see why during the talks, because there are lots of things that you have to consider. Now, but let's go focus on the physics. So that's that. But if you want this to happen all the time, you need to pump the line, what we call, which means to excite the line all the time, because otherwise you will not see emission in this line, Now, if these two states, this is an ideal line for Einstein model, this A and B Einstein modeling, because this is two-state system, period. There's no kind of fudging around. So Einstein A and B, they are all here. If the two are in thermal equilibrium, then the ratio between the populations in the excited state versus the ground state is given by a Boltzmann factor. And the Boltzmann factor is written in this way. I'll explain what comes into this Boltzmann factor. First of all, you have the temperature of the transition. I know what the temperature of the transition. It's a 21 centimeter line. So we know the frequency, we know the energy. And this is what the energy is refers. It's almost 5 micro electron volt. It's tiny. This is called the spin temperature. And that's kind of the effective temperature of the system, if it's in thermal equilibrium, okay? So this is the Boltzmann factor. I think this is energy over energy. You know this. This is easy. But we write it in terms of temperatures. Normally, you will see why we like temperatures rather than energies, just because of historic reasons and astronomical reasons. The 3 comes from the fact that this state is a triplet state, and this state is a singlet state. Why? You have 2 antiparallel spins. Then the sum of the spins is 0. It's 1. And you have here 2 parallel spins. The sum of the spins is 1. Then you have 1, 0, and minus 1. All right? So this is the triplet, and this is a singlet. So the statistical weight of this is 3 times this. That's why the 3 is here. Okay? So that's what we use. Now the question is how you pump the line all the time, how you excite the line. And this goes back to some of the things I mentioned before. Okay? So, now, it turns out that and this is basically all in this paper, in this 1958 paper, but then these are the modern kind of more advanced versions of it. So the question is, let me before the question, let me mention one important physics fact. This is under the condition of thermal equilibrium. However, in many cases, we don't have thermal equilibrium, right? So this formulation becomes a bit iffy. But still, we use it. And instead of talking about ratios of populations, the ratios of the population in the thermal equilibrium case is given by this only free parameter, the spin temperature. This is what we call the spin temperature. When there is no thermal equilibrium, we still use the spin temperature as a shorthand for the ratio of populations, right? It might not follow the Boltzmann equation anymore, but it's still, that's what we mean. When I talk about the spin temperature, I mean what's the number density of this case versus this case? How many atoms in this? Okay. Now, Field asked himself how we pump the lines. And the line can be pumped by a number of processes. The first way to excite this line is the CMB itself. CMB is a Planckian. It has a very long tail of very low energy photons, including photons that correspond to that transition. So it can absorb it and get excited. So the CMB should be here. By the way, this is the formulation in a more recent, kind of the second or third paper that he wrote on the topic. In the first paper, he wrote it in a completely different way, but not completely, without the minus ones. But he reached a conclusion that with the minus ones is better, so that's the first excitation mechanism. The second excitation mechanism is the Lyman alpha. It's this mechanism that has a few paragraphs of papers written on there. Is this Wauthausen guy. All what he said is the following. In order to excite the line, you can have a Lyman alpha photon. That's the cross-section is very large. So if you have a Lyman alpha photon in the ground, the hydrogen atom will get excited to its Lyman alpha level, and then it goes down immediately. When it goes down, it prefers to go down where you have 3 states of, instead of 1, the excited state, which has 3. It has more statistical weight. So that's how you pump the line. You go to Lyman alpha, and then you decay, and you decay preferably to the more excited case. Okay? So that's the first thing. So that's what you see in this equation as X alpha, Lyman alpha. There is another way to have excitations is through collisions, through just energetic things that go on. And those, I'll spend some time explaining what collisions can do. But again, it has this factor here, X alpha and XC. And these factors you can derive them from Einstein equations of the 2 population case. And notice this has no factor in it. because he assumed it's 1, and he renormalized those with regard to it. You can do that. There is a freedom here. So these are atomic physics type of things, okay? There's another small comment I have to make here, which is that the temperature is the kinetic temperature. Here, you see here the CMB temperature, but this is the kinetic temperature, the gas temperature. Originally, he wrote it in a different way. He wrote it as XC, TC, collisions. There's a temperature associated with collisions, but you can show that because Lyman alpha is so efficient, even if you have collisional temperature, it immediately thermalizes with Lyman alpha, and they have the same temperature, except in very extreme kind of conditions. Okay, so that's why I use the same temperature in both. Okay? So this is, because remember, I'm not talking about things in equilibrium necessarily. So if they are in equilibrium, all will be the same temperature. But in this case, the temperature due to collisions and due to Lyman alpha thermalize quickly, and they have the same value. So this is what sets this number, the spin temperature, which tells me how much excited versus how much is in the ground level. It also says something very simple in terms of physics. What sets the temperature is a competition, basically, between the CMB and the gas temperature, the kinetic temperature of the gas. Sometimes this win, then the spin temperature will be like the CMB temperature, sometimes this win. Now, we need this to win, because if the CMB wins, as you will see from the equations later, it's like looking at just wanting to observe a red dot on a red background. You just don't see it, right? Because we have this thermal bath of photons that coming from the CMB. It has certain temperature, so if you have something in front of it that has exactly the same temperature, good luck, you will not see it. Okay, so that's the game. Clear so far? Okay, very good. So this is this is the effect that Wauthausen talked about in these 3 paragraphs. And if you go to Field paper, you will not believe that this guy, had an effect after him after 3 paragraphs, because the details are really, really very extensive. So we call it now the Wauthausen field effect. That's Lyman alpha pumping. Okay, we'll come to collisions. Now, collisions are also important. You can excite lines, you can ionize lines by collisions, or thermalize things by collisions, have a different temperature. And there is which type of collisions are the more important? There are so the most important is these HH collisions, it turns out. In certain cases, electron, hydrogen, and these are very important in X-rays. They are very important. So in galaxies, this is the dominant. In our 21 centimeter in the intergalactic medium with X-rays, that is what's important. It's basically electrons colliding with atoms, and they do. I'll spend some time on this effect a little bit, because that's important. And this effect of exciting things due to collisions with electrons can do 3 things. It can excite from Lyman alpha to Lyman beta to et cetera, et cetera. It can ionize. You can, hit it so hard that the electron basically gets out, so you ionize it. And the third effect it does, it basically thermalizes things. It basically heats things a little bit, right? You have an energy you dump into a medium, and its temperature goes up. And you will see during this talk that this is related to X-ray sources. I'll tell you what the physics is, but I'll go in details a little bit later. Why the X-ray sources are related to this? Because when you have a Lyman alpha, you have a Lyman limit photon, ionizing photon, 13.6 electron volt photon, that a hydrogen atom absorbs. The electron that gets ionized have barely any energy left to do anything. So basically, because it's just all the energy of the photon went mostly to the ionization, and a little bit is left for the kinetic. However, if it absorbs an X-ray photon, let's say 1 keV photon, this 1 keV, this 1,000 electron volts, lose about 10 electron volts, 13.6 electron volts, right? But so the electron comes out from this atom with a huge energy, with 1,000 electron volt almost. And so it starts bumping, and so these are called secondary electrons, and these secondary electrons do this, right? They do ionize, they do excite, and they do thermalize things, heat things. Okay, so I'll come back to this a little bit quantitatively later. Now we come to the observational side. What do we observe here? I'll not talk about observation too much, but I need to talk about the brightness temperature, which is part of the physics. Now, to remind you what the brightness temperature, if you haven't learned any radiative transfer course, the brightness temperature is the normal temperature. If you have a black body in the Rayleigh-Jeans tail, if you remember, the intensity goes like the temperature multiplied by nu squared, by the frequency squared. If you identify the temperature by the ratio between I and nu squared, that's what we call the brightness temperature. So if you have a black body radiation, the brightness temperature is the real temperature. But even if it's not, so we call it the brightness temperature. And if you notice, it's basically measures the intensity of photon. It's basically a measurement of the intensity up to nu squared, right? So when radio astronomers talk about the brightness temperature, they basically talk about how much photons get to their telescopes. It's not a mysterious temperature, it's the intensity, right? At a given frequency. Of course, they have to normalize it by nu squared with all kinds of factors, but this is what it is. That's why radio astronomers use this term brightness temperature, because it's very low energy stuff. It's really even if it's Planckian, it's in the Jeans tail, and what they refer to is their intensity. Now, so this is the brightest temperature. This is the differential brightness temperature, because as I mentioned before, what we need to measure is the differentiation between this, a difference between this and the CMB. So you take the CMB, or the photon temperature, which is in this case the CMB, out, and you get this. Now, this is intensity. Again, you should go to intensities here. If you go to the book of Rybicki and Lightman and ask what is the solution for a medium that has a constant spin temperature or constant intensity inside it, like this. Photons from here come. Some of them get absorbed, and some get passed. The others are, there is an emission here. You can have a solution if the emission here, the TS is constant across this cloud. And you can open, it's equation 30. I mean, I just looked it up before, not that I remember it all the time, but I just looked it up again before I got to the lecture. This is the solution. And you can understand what the solution is. Let's assume that tau is 0, right? If tau is 0, this is the emission, the transmission probability, if you remember. Tau is the optical depth. If 0, it means there's nothing gets absorbed. All this will go through this, and this will be 0, right? There's nothing, so the interaction will go by, and there's no kind of feedback. Take another example where the two are the same temperature. Then the sum is the same temperature, right? Because this and this cancel. I'll give you 1. This equals to this. This gives you Ts, or T gamma. This is like looking at a red dot on a red background, right? So this is it makes sense as a solution. You can look it out. This is the solution of the radiative transfer equation in this case. And from these two, you get this. So far, so good. This is the spin temperature, the shorthand for how much excited versus how much in the ground state, and this is the CMB temperature, right? This we can hopefully work out due to these processes and this is, we know, the CMB. What is left is this tau. So what's this tau? This tau is a simple thing. It's the cross-section for excitation, or going from ground state to excited state, multiplied by how much of those there is, how much is absorbed. This is the factor of absorption. This is a factor of transmission. This is a factor of absorption. So how many of the photons from the CMB get absorbed here? And again, this is simple. This is how much excitations from 1 to 0. This is the T star that I showed you before without the K, over the spin temperature multiplied by K, right? And this is the line profile, right? This is standard atomic physics, multiplied by the number density. In the optically thin, which is the stuff we are interested in, limit, this you can write as very small, and then you can solve, you can put this as 1 minus T nu, and just expand it as a Taylor expansion. So, Okay, so let's focus a little bit on this T nu. You can show that T nu roughly is under generic conditions is proportional to this. It's h nu over kt. This comes from expanding this. Okay, assuming that Ts is much smaller than much smaller. Yes, than the energies. Then you get this. Sorry, this is much smaller than this. You get this. This is from the expansion of this. And then you have an integral over line of sight of n0 that gives you the column density of H1, right? The factor of 4 happens because only 1 in 4 electrons is in the ground state, right? You remember there is 1 versus 3, so 1 in 4 is in the ground state. And this is multiplied by the line profile. And if you remember if you had a course on these topics, the line profile is set by 4 effects. One is the quantum kind of profile. The other one is temperature, turbulence, and pressure. So the quantum one is what we call natural. Thermal broadening is a Gaussian thing. Turbulence and pressure gives you Lorentzian type of thing more. Pressure gives you Gaussian. Turbulence gives you Lorentzian, and natural gives you Lorentzian. So to be clear. And the integral on this, kind of line is 1 basically. It's normalized to 1, so that you get. So this is, we have an equation now. Look what we did. We have an equation now for the cross section, which we still don't know, but we'll calculate in a second. Multiplied by the frequency over the spin temperature, multiplied by the column density of hydrogen, neutral hydrogen. So it's all astrophysical things that we can measure. And the cross-section you can calculate from Einstein kind of transitions. And it's related to A10, Einstein A, right? The decay. And that has a units of 1 over second, and its value of 10 to the minus 15 per second. That gives the line its lifetime. 1 over this is roughly the lifetime of the line. And that's 10 to the 7 years, right? Roughly. In a year, there is 3 times 10 to the 7 seconds. And you need another 10 to the 7 years to get to 10 to the 15. Okay? Great. So far, so good. Let me see. Okay. Still fine. Now you can approximate. I will not get into too much details here. I'm realizing now that I'm maybe going too much details. So you have some approximation of the line profile, that because of the expansion of the universe, you'll have that imprint on the line profile. That's what you have H here. Delta S is so that's the line of sight that it covers. XH1 is how much H1 you have. If you don't have H1, it should be 0. And delta S is the line element, basically, width. And you put all of this back in the integral, and you get this, right? This dV dH, it comes from the H expansion. That's the kind of deviation from the Hubble flow, and this is what you get. All what you see in this, there's be a complicated equation that we all show it immediately when we start giving seminars in this field, which is very complicated. It comes just from calculating tau in under cosmological conditions. This we know, this we know, this we don't know. You put all the constants, and you have a number of fields here, and this is what you get. So here I've kind of filled all the constants. 1 plus delta, I turned n, which was, where was n? It's here. N, I wrote it as the mean density multiplied by 1 plus delta, which is what we do in cosmology, right? So that's where this delta comes from. The 1 plus z to the 3/2 comes from the h. So you have to, because I kept h here, so you have to do it properly. And then you get this ratio between xh1, that's the field of ionization fraction. So ionized fraction is different from one point to each other. This is not a mean value, this is a field. How much H1, this is not ionization, this is neutral, 1 minus this is the ionization. This is the neutral fraction of hydrogen at any point in space. Okay? Multiplied by this. So now we go back to this. Oops. And just substitute tau nu. Basically, we have now worked it out. What is tau nu? And you get this. This is the famous equation that we all use. The brightest temperature is this. And it looks daunting a little bit because it's a complicated equation, but let me simplify it for you a little bit. First of all, it sets this has to do with the constants and the mean density at redshift 10. So here I am assuming, redshift 9 to be accurate. So this is redshift 9. So this number, it depends on the cosmology and the quantum constants. This sets the scale of the problem. It's tens of millikelvins. That's what we're looking at. Tens of millikelvins in radio astronomy, not in CMB, in radio astronomy is incredibly tiny. It's a small, small, small effect, okay? So this is a very small effect. It tells you this is a difficult problem because the noise will be more, other effects will be much more. Now, what we measure is proportional to 1 plus delta, which makes sense. The more density you have, the more number of H1 particles you will have, right? The more ionizations you will have, the more excitations you will have. Therefore, what we measure is proportional to the density. That's that. It's also proportional to the neutral fraction. If you have ionized universe, you don't see this effect, period. So this is also makes sense. So this is a number between 0 and 1. This is a bit more complicated. I'll spend some time explaining it in the coming slides, but let me tell what it is first. It's the ratio between the difference between the spin temperature, you remember, how much is excited versus in the ground level, minus the CMB over the spin temperature. And this is very important in the cosmic dawn. So this is a school about cosmic dawn, and that's where I want to emphasize this. In the cosmic dawn, before the cosmic dawn, let's look at this term. This term has two limits. One, if the spin temperature is much larger than the CMB. The gas is way hotter than the CMB, which happens up to redshift 6. That's clearly what happens, right? And even above that. The gas in the IJM is of the order of 10 to the 4 Kelvin, right? That's the 1 electron, 13 point something electron volt. And the CMB is much smaller than that. If this is the case, if this is much larger than this, then this term is 1, right? You will see that in most of the epoch of reionization, in the case where we discuss the lowest part of this 1 billion years, the lowest redshift part, this term is 1, and it's not interesting. However, if you have a case where the IGM is still cold, and we'll get to why the IGM is cold, and the CMB is hotter, larger than this, this can be, first of all, it will be negative, because this is negligible. So we'll see it in absorption. If you heard about the edges effect, this is what they saw, absorption. And the ratio can be 1,000. There's no problem, because the CMB can be 1,000 times more higher than the IGM. You will see that in a second. Why is that? So this is an interesting term. These are all things that have to do with cosmology, redshift. This is interesting because this has to do with peculiar flows, so this is a redshift, etc. But so the problem is very rich. This stuff touches about cosmology. If we manage to measure those things, will tell us about cosmology. For instance, when we talk about dark ages, which we'll define in a minute, I'm sure you heard the terms, you are mostly probing this density, which is exactly what the CMB does. In principle, this is even more efficient than the CMB, if we can see it, but we can't so far. So this is cosmology, while this is astrophysics. This tells you how much ionization you have, ionization sources, what's their properties, etc., etc. And this tells you how much heating and cooling you have due to these sources, right? So this is astrophysical. And unfortunately, in a way, if you are a cosmologist and want to know about the universe, what we explore with ionization is mostly this. With the epoch of reionization is mostly this. What we explore with cosmic dawn is mostly this. to get to the cosmology, you need to go in a pure way. Of course, you can have cosmology in the back door. You have to go to dark ages, right? Then you probe this, which we hope to do. So the interpretation might be very complicated because it's a complex function, but you can see that at different stages of the universe, you probe different things. So if you can measure it at different redshifts, you have a treasure trove of measurements. That's clear. The other thing I want to mention before I move on, this is the IGM. What you guys are doing, galaxies, is interesting, wonderful. This is what we see. These are tiny, tiny, tiny points. The relationship between what you see in the IGM and the galaxies, that's up for grabs. I mean, it's a complicated relationship. So this probes most of the gas. And it's interesting. Why is it interesting for reionization, for instance? Because you probe this. You see it disappearing bit by bit, right? This becomes zero slowly. Okay, so this is the, something happened. Yeah. Right. So now I'll talk about the three eras. Now, the three eras that I'm talking about are the Dark Ages, the cosmic dawn, and the Epoch of Reionization. They define the first billion years. And I'll show you how we define, I think the best line to this, the best observational option to define the three of them is through H1. Because you don't see the differences in galaxies. Either you see a galaxy or you don't see a galaxy. Here we see different effects. And that's why we, so let me just tell you why. So this is the way it works. And I'll explain this in a couple of slides bit by bit. So if you look at the temperature, we talked about two temperatures here. The CMB temperature, right? And the kinetic temperature, the gas temperature. The question is how they are related and how the spin temperature to each of them. You remember the spin temperature goes, it's a competition between the two. Either the CMB wins and then the spin temperature is there, or the kinetic temperature wins, then the spin temperature is there. This is a figure that I did long ago, but many others did some similar figures. So, but the pressure than low starts more quantitatively. This is the temperature as a function of redshift. The blue is CMB, and the blue falls like 1 plus z. The temperature of CMB is proportional to 1 plus z. The question is, what happens to the gas? That's done in the next one. It turned out that the gas, even after decoupling, in terms of temperature, stays coupled to the CMB. Why is that? Because there's Compton heating. So if you, I kind of confused things, but I'll come back to this. Compton heating tells you how much temperature from the CMB goes to the gas. And that is proportional to this. So this is the difference between the CMB temperature and the gas temperature versus the time scale for Compton scattering. This is how much heating happens. Before going through this, a condition of this happening is that the kinetic temperature is smaller than the gas, that's CMB temperature, right? So why is that? So I'll go back. I think Andrea mentioned it in his talk. Why the gas temperature is smaller than the CMB temperature after decoupling? It wants to go smaller. It's very simple physics. So here is the calculation. You assume an ideal gas, you have this relationship, which goes to this. This is the equation of state. PV equals nRT, right? nRT. You substitute instead of P this, you get this. It's just very simple. And then you work out what's the temperature. The temperature is 1 over this. So this is gamma minus 1. But the volume is proportional to the scale factor, the universe scale factor cubed, right? It gives you this. Now, for a monoatomic ideal gas, this is 5/3. You plug it in there, you get this. The gas wants to cool faster than the CMB. Just the adiabatic expansion, make it much, much kind of colder. That's an effect. It's an important effect that people have to remember. Without heating sources, without shocks, etc., adiabatic gas cools faster than the CMB, much faster. If you calculate what the gas temperature should be today, if there was no astrophysics and no hydrodynamic effects other than adiabatic cooling, it should be 1 in 100 or 1 in 200 of the CMB temperature. It will be tiny, right? 3 Kelvin, it will be 0.006, 0.001 Kelvin or 0.01 Kelvin. It's tiny, it's nothing. Of course, we have astrophysical processes that heats it up. What heats it up is the Compton heating. Right, so the kinetic temperature wants to be smaller than the CMB. So this is always positive. And these are just NE, KB, and T components. So when the universe expands, so immediately after the recombination, this heating is dominant. So you keep the gas temperature tied to the CMB, the same temperature. So the poor spin temperature that tries to kind of run away from one to the other has no place to go because it's immediate. It's just both of them are the same. With time, two things happened. One is that the density of electrons goes down because the universe is expanding. So the electron density goes down like the scale factor cubed. And the other thing is the Compton scattering timescale, the Compton timescale, the Compton cooling time or heating time also changes because it's inverse proportional to U. U is the black body radiation spectrum. So at some stage, this stops being important. And you can calculate where that stage is about redshift 200. So from redshift 1,300 to redshift 200, the gas and the CMB have the same temperature. So you cannot see anything there. And so that's what's written here. There are codes that are available to calculate this. So let me go back. So this is this part of this figure. I'm taking my time here. Normally, people don't talk about this. They just mention it in half a minute and half a second. And things start so the gas here immediately after 200 start cooling because Compton heating stops being important, and then it cools very rapidly because it goes down like 1 plus z squared, not like 1 plus z. Okay, so it goes down very quickly. Or I should say, it goes up like 1 plus z squared. It goes down by the other side. And so the poor spin temperature, what does it do? Then it kind of gets confused. Where should I go? At the beginning, there is still Compton scattering, enough to tie it to gas. And then after a while, that also becomes not important. And then it starts veering towards the CMB. This period, where the spin temperature is seen negative to the CMB is what we call in 21 centimeter the dark ages that we can measure. Of course, the dark ages was defined differently. I'll tell you in a second how it was defined. This is the period of the dark ages. Now, here comes the first sources that we have. You guys have been talking about for the whole week. The first sources start heating stuff, start ionizing stuff, start coupling, emitting Lyman alpha. So they are very good at Lyman alpha. So now follow the dashed line here. Lyman alpha start coupling the spin temperature again to the gas. But the gas is no longer going down like this because it's also heating up itself. So this thing goes down, joins the gas, and then ionization becomes much more important. Heating becomes much more important, and this goes up to the. This period here, where you see it again in absorption, that's the cosmic dawn, because this has to do with the first sources. And once you are dominated by sources and ionization, you go into this positive thing. Your temperature becomes very, very large. Your spin temperature becomes very large. CMB becomes, you neglect it. And that's the epoch of reionization. And this is done in this famous figure from Richard and Loeb. So these are the dark ages. And you can see they stop at 80 here, but you can go to about 200, 150. That's the right thing. then it veers back, but then UV bumping from the first sources start being important, and it couples it to the gas. Remember, the gas is very cold at this stage, right? Because there's no heating. But then X-ray heating and other effects come back, and then you go up and you go to the epoch of reionization. Now, this is, remember, this is a model that have a number of assumptions about when the first sources happen. This might go like this. We don't see this cosmic dawn in 21 centimeter. There's a crazy models that this happens in there, okay? So this is the picture, and these are the three eras. Dark ages, cosmic dawn, epoch of reionization. Epoch of reionization because it's the ionization bubbles or kind of regions start being dominant until they control everything. This is because the first sources start popping up. That's cosmic dawn, first light. And this is dark ages. Now, dark ages, why it was called dark ages? It has a cute reason, okay, and another kind of historic fact. It was dubbed by Walt Sargent, actually, and it was made popular by Martin Rees. What he argued is the following. What he argued is the following. If you are alive, if we exist at redshift 1,300 when the decoupling happens and recombination happens, the temperature of the CMB would be of the order of 3,000 degrees. That's visible. We can see that. The sun is 6,000 degrees, right? So this will be kind of yellowish. The universe will be yellow if we were alive there. But then bit by bit it expands and it goes out, it gets redshifted and becomes dark very kind of slowly, relatively, but it's quick because it's a function of redshift. It's slow, but it's a function of time. It's very quick. And then we go into a period of darkness. That's why he called it the dark ages, right? So, because there are no sources, there's no light. It's the darkening age. There's a famous book about Christianity called The Darkening Age. So recommend it, but not in terms of science, in terms of other things. Okay, so these are the three effects. And I think that this is the best way to define the three things that we can observe. Beyond 200, I don't know of any way of observing the dark ages. There's no way you can observe the dark ages, except if there is very primordial things. And even then, it's very hard. Okay, good. Questions so far? I'm kind of running a little bit. Yes, please. Here? Yeah. So here you understood it, right? Yeah, so this is because you have still really Compton scattering. That's not good enough to heat, but good enough to couple, because the coupling is much easier. Here, you have the first sources. The first sources start producing Lyman alpha. Lyman alpha can pump the line, if you remember, with this Wauthausen field effects. If it can pump the line, it means the spin temperature gets coupled to the gas. But the gas is colder than the CMB, because it hasn't had time to heat. There are no X-ray sources yet, etc., to heat it efficiently, at least all of it. So the spin temperature starts veering towards the gas temperature. But at the same time, there are more sources and more heating and more ionization happening that the gas becomes hot itself. So it gets coupled and it stays with the gas until it goes up. Okay? More questions? Yes, please. Oh, this is so before the Pritchard and the Loeb paper, I think most people were thinking in these terms. So there's no, the first thing you see is ionizations, which is that was an oversight, and this is actually the more, but there is still an option of going like this, right? There are some models that do that. More? Okay. Right. So this is just a figure from a couple of, I think this is done by Messinger et al., by Andre, and I think it appeared also in Kopmans et al., where you see how we should see the universe. So you see, so the red is absorption. So this is dark ages, basically, and you go into darkness, again, because the CMB and the 21 centimeter is coupled to the CMB, so stop seeing it. And then the first sources start coming. You have another absorption feature, and then you go into the ionization. Notice here there's rarely any ionization. Ionization is here, basically, and towards the end of it, you ionize everything. You stop seeing because of the ionization. Okay, so that's the history of the universe that we would like to see. Here, the only fluctuations are the fluctuations due to the density. So if you can see the dark ages, you have a direct probe of the primordial density field. like the CMB. But the difference here, many redshifts, right? So it's, in principle, it's more richer, but you know, it's much more difficult, so it doesn't make sense. Okay, now, dark ages, and this is a theme that is very hot now. So back in 2020, we wrote a paper, it was led by Leon, so that's this paper. We wrote a paper entitled "Peering into the Sky with 21 centimeter," or "Peering into the Dark Ages with 21 centimeter," or something like this. And the whole point of this paper was to say we have to go to the moon if you want to see the Dark Ages. And now, why? And this is actually was pointed out earlier by Loeb and Zerriaga, but others as well. The reason this stuff is difficult to measure from Earth is that you have a number of effects, foregrounds, that basically kill you, but the most important things that kills you is from Earth itself. So this radiation is tiny. I told you it's millikelvins, tens of millikelvins, or sub-10, actually, a little less than 10 millikelvin. We have emission from our galaxy, which is synchrotron emission, which is huge. It's of the order of kelvins, 1,000 times more, right? Or even, so the fluctuations are of the order of kelvins. The absolute thing is about 100 Kelvin, so it's 10,000 times more. So you have to kind of sift this thing from a mountain of foregrounds. But not only that, when these things come to Earth, they get scrambled by the ionosphere. The ionosphere is the enemy here, and this will be part of the focus of the talk tomorrow. And if you go down to frequencies of, if you remember, I'll go back to this figure. Yeah, I think it's here. These are the redshift, and these are the frequencies. So these are the frequencies that you want to go. No, this redshift. No, sorry. It's this one I want to show. This one. So to go here, you need redshift 80, 30 to 80. In terms of frequencies, you have tens of megahertz. The plasma frequency, of the ionosphere is of the order of 20 megahertz. The ionosphere becomes reflective at these types of things. This is the same reason we can listen to radio, right? Waves can bounce off and come back because of that, right? That's why you listen to the US in radio, because it bounces off the atmosphere. So it's the opposite effect. Things that come from space cannot penetrate the ionosphere. And if you want to go to this type of frequency, which is very, very low and very difficult, you have to go to the moon. And that's because of the ionosphere. The ionosphere not only reflects, it's not unstable. It's a dynamic entity. You have to solve it quite, and it's a hard problem. This is the main problem that we are facing. So that's why people suggested that we go to the moon. Not only to the moon, dark side of the moon. Because facing Earth is not good. The Earth we produce. So we did this exercise. So there's one of the nice exercises. I told you in interferometers, which we are using. I'll come back to that. This is a kind of a little bit digression. In interferometers, you measure differences. So you have to measure differences. So one way to measure the temperature of the sky versus, you need to compare it to something. One way is to look at the moon and compare the moon versus, if you know the temperature of the moon at these frequencies, you can measure the temperature. It turns out that it's difficult to measure, to define the temperature of the moon. It's varying, etc. But it's a kind of, you can do something. But if you look at the moon, what a PhD student spent part of his PhD on this. You see at the center of the moon a huge signal. That's the reflection of radioactivity on Earth. It kills everything. It becomes the. So that's why you have to go to the other side of the moon, because to block us, because we are very active in radio. So it's by far bigger than anything. So when we wrote this paper, this was written for Voyage 2050. I forgot the ESA program that has Voyage 2050 or something like this. In 30 years, we will go do this. But then the Chinese and the Indians went to the moon. Now this is acute. The people are really, within few years, people will fly things to the moon, right? It's not driven, it's like always, it's not driven by science. We are using it, it's driven by politics. I know that your colleague that's responsible is my friend. So there is this, Chinese have this satellite interferometer around the moon. Actually, this is an American idea. Before this, there was this DARE Institute, Lunar Institute, which has this project called DARE. There's lots of activity in this. So I will not talk a lot about this, but dark ages are, in principle, can be detected if you go to the moon. I am too old to see this, but you guys are young, maybe you can see them or being active in this. Right. Let me now go and also talk about, so here, again, I'm talking about basics. So many of these papers are old, but I want to talk about the effects. I mentioned the effect so why there is a difference between thermal sources, like stars, and power law sources, like black holes, right? You hear this a lot, Lyman alpha, pumping and heating, and all of the X-rays are important for heat. And so why is that? So I explained it a little bit, but let me go into details. The mean free path of a photon for Lyman alpha, basically, for ionization, for bound free, basically, cross section, it goes like this. This is 1 over the hydrogen number density, the sigma of sigma of this Lyman alpha of the bound free effect as a function of energy. And one thing that you notice immediately, that the cross section for bound free for hydrogen goes roughly like the energy to the -3. This is not accurate. This is roughly. I should have said roughly here. It's a bit 2 point something, but it's roughly -3. Which means, and it starts from a certain energy. Energies that less than 13.6 don't ionize, so there's no bound free there. So from 13.6 electron volt and up, this is how it behaves. So if you have a photon that has 13.6 electron volt energy, it can ionize, but barely any energy is left for heating and other things. But the cross section is sigma 0. However, if you have 1 keV photon, right, it's 100 times more energy. It has a cross section of 1,000,000 smaller. So X-ray photons are not very good for ionizations. They are not very efficient. That's why they penetrate so much. So that's their strength. They penetrate the IgM. They go out from. That's why X-ray always you see outside, right? Because it doesn't get absorbed. Because the cross section is very small. But eventually it will, because the universe is big. Once they get absorbed, they dump a lot of energy there, heating. So the influence of X-ray sources is felt very far from the location, right? And so this is many people did these types of papers, but these are the numbers here. And again, this is just made in. So for a UV photon, you ionize, but the energy, the particle looks very, very big. The cross section and the velocity, this should be here actually, and the velocity of the electron is quite large. Whereas in X-ray cases, the cross section is tiny, right? But if it happens, the velocity of the electron is quite high. In a famous paper written by Schull and van Steenberg, who looked at X-ray secondary electrons, these electrons that are they looked at, so Schull and van Steenberg, and then later Andrea and one of his students, Valdez, looked at this, made the more accurate calculations. There are 3 effects, there are a number of effects that they looked at. I'll forget about the helium for a second. This is the total energy. This is the excited. So again, these can excite hydrogen. They can ionize hydrogen, that's the phi, and they can heat. And these are the 3 effects. And you can see that as a function of the ionized fraction. And you can see that when it's roughly reasonably ionized, it's about 1/3 of the energy, 40% of the energy goes for excitation, and 40% goes for ionization, and a little bit less goes for heating. So when it's 1% ionized, then you get this, right? So it's quite well-studied thing. So you take this and ask the following. This is a work I did in 2008 with one of my students. Again, the reason I'm showing this is because it was very simple just to show the effects. So we looked at stars and black holes, and it asked, what is the difference? So I assume there is one object in the universe, and this is a black hole. So on third, line alpha, this is a black hole, 20. What happens to ionization? The difference is the ionization front, and here is the difference between the heating.
It's rather hard to see the curve.
One of them. Can you see this? One of them. The others are not important. It's just focus on one that you can see, which is, I think, the dashed one. And, or the black one. Just look at the black one, solid one. And you can see that if you look, I mean, the black one here is very difficult. If you have a thermal source, the ionization front is always very abrupt, right? There is always, it's like a Stromgen sphere, except it's in an expanding universe. So there's an abrupt ionizing front. Here, if you look carefully, there is a structure for a black body, a black hole, a thermal power low. There is a bit of a structure here because the border is not very clear. It's not done by the 13.6. So it gets more expanded, right? So there's more subtle. However, that doesn't happen in real black holes because this needs time to thermalize. So in both cases, you will see a very abrupt black hole. However, in that heating around them, you see a lot of difference. So this is the heating. This is the temperature, kinetic gas temperature beyond. So this is inside the ionized region, and this is beyond the ionized region. And you can see there's a sudden drop. With a black hole, there's this, kind of gentle drop. That because the X-rays are penetrating and heating stuff. So this is what we talk about when we talk about X-rays, heating stuff. Okay. And now, how is that translated to in terms of thermal energy? Again, this is a black hole now. I'm just talking about the black holes. This is the brightest temperature. Inside, there is no brightest temperature because it's ionized. This is as a function of radius. And then suddenly you get a positive, and later you get negative because the gas is very cold, and you just couple it, nothing else, and you get negative stuff. So this is the fluctuations in this term, which is very complicated. Ts minus TCMB over Ts. That is and this is a simple case of one thing. So you have to take that into account when you do simulations. And how much time do I have?
Well, you have
20 minutes.
So if you want to have questions.
Yeah, 10 minutes. Okay. Now, okay, so I hope I gave you a flavor of the physics. So I'm done with the physics of the line and how it affects things. Now let me tell you how people try to study it. The logical thing to do is the following. Take a cosmological simulation. It has to be cosmological because we are talking about big things here. But it has to have an incredibly high resolution to resolve the sources. And then assign spectra for the sources, SEDs, spectral energy distribution. And actively follow radiative transfer equations that follow the ionization and heating effects. Good luck doing that. Almost no one does that. It's just impossible. I mean, you can do it on a very small patch of the sky dynamically. All of these effects dynamically, it's very hard. So what people do, so there are some people who do the high resolution, everything. Well, that's tiny, and then you spend millions of hours on a high HPC, on a high performance computer, and you get a small patch, and then you say, oh, maybe this model is wrong, maybe I have to like that. So you have to do it again and again. So nobody follows radiative transfer dynamically, almost nobody. I mean, there are some people who do that, but then you cannot do much. The main thing that you do is so you need this hydro, and you need out of equilibrium radiative transfer to do. So many people do, you cannot do this in tandem, together, dynamically, as I said. So what you do, you run this, and you do this in post-processing. Right? Use basically step processing. You miss in some places because sometimes radiative effects are important for the dynamics, but most cases you are not. So this is fine. Still, it's very difficult, because you need to explore these types of things. You need to resolve the sources, and you also need a huge chunk of the, hundreds of megaparsecs of the sky for all kinds of reasons. You need cosmological things. So those are very done and very good. People do these, but once in a few years you hear about one big simulation like this, and it has its own parameters, and that's the limit. However, if you want to go beyond that, so let me show you before I go to this is a famous example of how ionization progresses out of one of these simulations. This is done by Marcelo Alvarez, and you can see this is a cube of simulation. You will see that it's a cube in a second. That ionization regions start being carved out. And you can see that at the beginning, these strong ionization sources have these bubbles in between them. But very quickly, they start to have networks of open things. And then the relationship to the initial sources start being not clear. Where this radiation that is here came from. Is it from here, God knows. And then bit by bit, actually what drives the contrast towards the end are these black regions that are not ionized, right? So the contrast is driven initially by the ionized cases around the sources, but towards the end, there is nothing. And this is what you see.
What do you mean by drive the contrast?
So imagine at the, at redshift 10, let's assume that you have a few strong ionizations. So you will have isolated bubbles. So the contrast in the power spectrum, when you measure whatever you measure, is driven by these bubbles, and they are associated with the sources. Towards the end, that's not what left. Actually, what you measure towards the end are the voids, and they are not associated with sources. The relationship with the sources is there. And we have this conceptual problem in the field that we go after the ionization sources all the time, and that's one of the arguments why you shouldn't. You should do both. I'll come to that tomorrow, basically. This is a big simulation that we did that was led by Ilian Iliev and Khalid Melema from Stockholm, Ilian Iliev from Britain, from Brighton, Sussex. And this was a postdoc who did this. This was run, it's actually an in-body simulation, no sources with no hydro, because it's too expensive. This was run on BRACE, the European thing. It was huge. And then, but we did the RT, the radiative transfer post-processing. And these are, so you can dress these halos with all kinds of sources, and this is different scenarios of ionization. And you can see that you can get different scenarios, and if we can measure these effects, we can say whether it's early structure formation, early sources, late sources, etc. One thing I want to draw your attention to is, towards the end of reionization, you always have these isolated clouds, right? Now, some people, and I think they are right, like Andre Messinger, claim that ionization remains not finished completely until redshift 5.3, 5.5, something like this, which is much smaller than we were thinking. And that, for me, creates a problem because at low redshifts, you don't want too many sources, because this is what we see from the CMB and other things. On the other hand, we see all of these sources at high redshifts. It's a conundrum. I don't know how to solve it. So another way to go is numerical methods, semi-numerical methods, and this is the most famous of them. Is 21 centimeter fast. It basically follows a kind of extended pressure sector type of recipe, where it says, okay, where things are collapsing, I assign a number of ions, I basically solve this equation where it says how many things are collapsing. I assume some baryonic fraction, some star formation rate, and all kinds of things about escape fraction and number of photons, etc. And relate it to the number of ionization, and you come up with this equation where it's the collapse fraction as a function of time gives you how much is ionized around them, and that's how you solve it. It's a very quick way to do things. Why this is important? Because this is so fast, we can explore thousands of ionization models. Whereas the big ones, once in a few years, we get one model, which is not good. So this way, we can make forecasts of different effects, like what we did here. Right? Sorry. like what we did here. These are different effects, but this is on a big simulation. It took us a long time to do this. Whereas in something like what the 21 centimeter fast, you can get things very quickly. So for forecast, for predictions, what you want to say is important. It's even more important for analysis, because you measure something, you want to ask to yourself, what I measure, what does it mean in terms of sources and ionization and all of that stuff? Then you need thousands and tens of thousands of models. Good luck running them with full. So you need these types of methods. This is one of the creations. So there is another, just to be complete a little bit, there is another simulation which is similar, roughly developed in the same similar to what Andrei has done. There's another one by Fialkov, right? That is similar. There were a number of them. 21 centimeters is the fastest. We, in my group, developed a different way. The different thing, instead of looking at crest sector, we said, okay, let's learn in body and look at high density peaks and ionize around them using one-dimensional spherically symmetric ionizations. This is also in use, and there's more activity in this nowadays. Other people are developing similar methods. We use it to analyze LOFAR data. And I'm going back, sorry. I thought I'm going down, turns out I'm going back. And this is one of these examples where we use the thermal sources versus non-thermal sources. So that's just to see what are the differences, and you can explore different physics. And in all of us, we have to calibrate against full simulations to see whether we do well or not. And this is an example of kind of doing, we do well. I mean, it's not bad. It's not, so in these approximate methods, and I think Andrei is doing this, we are doing this, all of us just compare with the full simulations to see whether these simulations do well, and relatively. So I talked about the spin temperature. To end, I want just to talk about final effect, which is the forest. So I told you about the bulk of the intergalactic medium. And this is what I will spend most of the time talking tomorrow. I want just to talk about one effect, which I will not revisit again, but it's another way to measure. You all know the Lyman alpha forest. So one can think, so Lyman alpha, what is the Lyman alpha forest? You have a source of Lyman alpha and, kind of a power law source roughly, or a continuum source. And as it comes to us, it gets absorbed at certain frequencies that are in resonance with the local Lyman alpha resonance as it comes to us. The same effect can be done in 21 centimeter. You can have a source that gets absorbed, basically the same. It's not exactly the same, yeah. So you have a source that has radio source at the radio emission at some stage, and then it gets absorbed with 21 centimeter line. And you get to the forest, if you can measure it, so this is a prediction that was made, I think this is from Karilli et al. This was the first predictions of these types of things. So you have a spectrum, and then you have a neutral. So the hydrogen has to be neutral, of course. It gets absorbed in these types of things. So you see this forest. Now this requires things. One is that you have a radio loud source, and radio loud black holes. And currently, I think there is none at high redshifts, right? Right, but it's very timid. It's one of these physics that we still don't understand, right? Why some have, low redshift has more. But that would be interesting. If you see this, then you don't need to calibrate anything. This is relative to each other, to the frequency, along the frequency. This is a function of frequency. So first you need to find a source. That's very difficult. And then you need to have the resolution and the time to see this. And all of these differences, if you have high temperature, this is more recent work that we did with Benedetta, and you can see if the temperature is high, you get crowding, and then it's very hard to see the lines. It's exactly like what happens with, the line becomes wider, and then you get overlap, and then I'm almost done there. So this is the stuff we did with Benedetta. You can see that it changes with temperature. This is different temperatures, and the lines have different width depending on the temperature. And I will stop here. I hope you understood at least the basics of 21 centimeter physics. And tomorrow I'll go to the difficult stuff, which is the observations, which is really difficult. Yeah. Thank you very much. Thank you.
Thank you, Saleem. Questions? Yes, Roberto?
Roberto.
On the, first thanks for the most fantastic discussion. For the 21 real forest to be seen against the background of Quasar and Harish, is that, I understand there are no supervised law, but there are some radio sources. I'm not sure whether they can be identified as a law, but with SKA, I was suspecting that the sensitivity is
Yeah.
even if the
Yeah, I mean, some of it is a matter of sensitivity, but some of it is a matter of broadening the lines with the temperature. So if you have it, and so that's physics of the surrounding. So if you have a cold enough IgM, you can do it. That's one thing. The other problem with these sources is to discover them. So you discover a few in high redshift surveys. The more efficient, they appear much more in radio. The problem in radio, they are featureless. So you see a source, you don't know what redshift it is, right? They are power law, synchrotron type of things, and it's very hard to know where it is in redshift. So yeah. So if you solve that will be. I think one of those, just one at redshift 10, can solve so many questions. I mean, it will be a Nobel Prize type of thing, I think. I'm not sure, but it's really a very important thing because you don't need to calibrate. Our main problem is calibration. Here, it's a relative strength. That's fine. That's much easier.
Sorry, one question here. So as you go to higher shift, the size of the lobes decreases just because the CMB temperature increases. So the very higher shift sources will be very compact.
Right.
Does the size of the source have a role in here? Or no?
No, I mean, you have, in principle, I mean, there's a resolution issue, but these are very high resolutions. So that's so high. I mean, you can, we use for the reionization baselines of the order of 100 kilometers in the Netherlands. But if you have a source like this, you can, in LOFAR, you can go to the European baselines, thousands of kilometers, and the SKA has even more. So you can have high resolution in this, much higher resolution than arc minutes. You can go to sub-arc seconds. That's fine, I think. Just contaminations, that's only. But you are right. I mean, even that alone is granted. If you have one source isolated and everything, it's fine. But you will have lots of contaminations in resolving from the ionosphere itself, etc. So it becomes it's a more technical problem, not fundamental problem. Yes, please.
What could we hope to see at redshift 100, and what do you know?
So what you see, if we can go there, you see the densities, fluctuations. And then you can ask questions about Gaussianity. Now, CMB is wonderful for that, but CMB is one slice in redshift. Modes of fluctuations, if there are some peculiar things, kind of particle physics effects, you can see them, mini halos that kind of have these. So the primordial black holes maybe that will affect things there. But it's mostly having a lot of information about the primordial fluctuations. And so Gaussianity, for instance, non-Gaussianity will be much easier in this way. And that's a very important probe of the early properties of the early fluctuations, whether it's gravitational or not gravitational. So all of these types of things.
So would you like to make a background at different redshifts? 100, 150?
Right. So if it's the vanilla model, the model that we are used to, then all what you will see is just one, the growth of linear fluctuations, because mostly they are linear. Of course, there will be tiny that are nonlinear, which will be much more interesting. But think about it differently. So there you just test the basic things. But it's the nature, the characterizations of the fluctuations themselves that become important. So why we look at galaxies and say they probe cosmology? Because at certain scales they probe the linear cosmological scales, and those we can connect to the early universe. right? So this will give you this for free at all scales that you can probe, right? And that's so even including very small scales, and that's very important, which we don't have access to in many cases. Right.
Or the baryon fraction that are just parameters.
Yeah.
Can they be made function of halo mass over
Yeah.
density?
Yeah.
Okay, so these are not necessary constants.
No, I mean they can be many things, and they have very I mean initially, for instance, they didn't have X-rays in them. Now they do. I mean for the 21 centimeter fast, so it's very quite kind of advanced. They take many of these. There is no association, for instance, with the halo. With halos here, it's just the press sector, right? So it's the collapse fraction, which is not. Yeah. No, it's this. I mean, you go through that, but that's the final one. And this psi kind of summarizes all of this, so you can change this to have a different type of dependence. So it's quite. I mean, 21 centimeters does very well actually.
If there are no more questions, since we're at 3:30 sharp, let's thank Saleem again.
Yeah. So.